I have physics test next.
Why do I have a mission?
Yeah, same.
Okay.
Like, it's not cool.
Hey, we'll deal with the grade book here in a few minutes,
I'm
okay?
just kidding. That sounded very like.
It was very sassy.
Why didn't you pick Justin?
Why didn't I?
These are like really nice.
I was just worried about getting things together to start.
I didn't put Justin in his place.
I kind of figured.
Yeah.
Appreciate you getting my back with that.
Yeah, he's swinging.
Okay. Today, we're going to continue talking about vectors. We have one more topic to talk about here in Chapter 8.
So that means the test is coming.
Yup. So what we're going to talk about is vector projections is going to be kind of the topic today. And before I kind of explain what this is, I want to kind of give some motivation for why we care about this, or what we're trying to do maybe. So what we're trying to do is be able to break a vector down. Maybe I should say A here instead of the. We want to do this breaking it down into orthogonal components. Boy, I can't spell. Orthogonal components. So we've done this to some extent already, right? If I took the vector 3, 4, I can rewrite that as the vector 3, 0 plus the vector 0, 4. Right? This is what we did when we wrote the vectors as linear combinations. If you can't read, you can turn the light off. That'll probably help. If ever it's hard to see the screen, you are always welcome to go turn the light off. So these guys are orthogonal. What does orthogonal mean again? Just means they meet at a 90-degree angle. So why are these two vectors orthogonal? Well, if I plotted them, the vector 3, 0 is here, and the vector 0, 4 is there. So those are definitely meeting at a 90-degree angle, right? What's the other way we can check to see they're orthogonal that's not geometric? If I call this vector u and I call this vector v, I know that u dot v should equal 0 if they're orthogonal. And it should be easy to see that those two vectors will give you a dot product of 0, because you'd have 3 times 0 plus 0 times 4, which does indeed give us 0, right? Now, this resolving these vectors into orthogonal components using this like unit vector idea is not tremendously helpful when it comes to dealing with problems in a real world. So we're going to develop another tool and procedure on how to do this. So this other procedure is called a vector projection. So let me kind of draw you a picture of what this process is doing. Okay? So let's say we have a vector here that I'm going to call u. And down here I have some other vector I'm going to call v. Okay. So what I want to do is I want to make like a right angle here. And I want to write this vector. This is what we're going to call the projection of vector u onto vector v. And the way we write that symbolically is we write PROJ, short for projection, and then the vector we're projecting onto is the subscript, and the vector we're projecting is written kind of in the same line. So this means, in words, the projection of vector u onto vector v.
And that's just like a small part of the line triangle.
Yeah. Yes. Okay. So if I call this guy vector w, what vector w is going to be u minus the projection of u onto v. So that is like that part. Sorry if that wasn't clear. So if I look, what can I say about the projection of vector u onto v and vector w? They are orthogonal. How do I know they're orthogonal from this picture? Because they meet at a 90-degree angle. Okay, so this kind of outlines my procedure for taking some vector u and breaking it into orthogonal components. One of them is the projection of vector u onto v, and the other is this vector w that I can find by just subtracting that projection from the original vector u, which is just like how we could find, if I knew this and this, how do I find vector v? Well, I can subtract vector u from the original, right? So that's the same idea that we're doing down there. Okay, so now that we've kind of explained geometrically how to do this, what we want is a formula So this is my formula for the projection of vector u onto v. It's the dot product of u over v divided by the magnitude of v squared. And all of that's just a scalar, right? The dot product gives me a scalar. That's a single real number. A magnitude is just a single real number. So I have real number over real number. That's a scalar. And then I'll scalar multiply that to vector v. So let's do an example with some numbers in it here. So we're going to find the projection of u onto v. And then we're going to express u as the sum of two orthogonal vectors, one of which is this projection that we just found. So let's start with the first part. Squared. So this is my formula for a vector projection. So I'm going to do this in kind of two parts. First thing I'm going to do is calculate u dot v. So I'll substitute in for vectors u and v. And then the dot product, we multiply the x components together, and then multiply the y components together, and then add them up. Everybody okay there? And then I'm going to find the magnitude of v squared next. So the magnitude of v is the square root of its x component squared plus its y component squared. And because we're looking at magnitude squared, I have that whole thing squared. Is everybody okay there? Well, this squared cancels that square root. So what I really have is just 36 plus 16. That becomes 52. Everybody okay there? Good. So my projection then is going to be 14 over 52 times the vector 6, negative 4. So let's see. I first noticed that 14 and 52 can reduce. Both of them are divisible by 2. So I can think about that as 7 over 26, right? So I'm going to get 7 over 26 times 6, and then 7 over 26 times negative 4. It's going to be my first vector. Now I can reduce that a little bit. 6 and 26 and 4 and 26 both reduce. So 7 times 3 is 21. And then 7 times 4, 7 times negative 2, excuse me, is 14. Yes, Kendall?
Why do you know we should put it into like the vector form, and then we should? What scalar would you use when you get one to the
Whether it's a scalar or a vector?
Yeah. Like for this one, did we leave it in vector form because we were multiplying it by a vector?
Yeah, so a vector times a scalar is always a vector.
Okay.
Now if you do a vector dot product another vector, that becomes a scalar. But any other of our vector operations result in a vector. So vector plus a vector minus a vector, scalar multiplication, those all give us vectors back. Projection of one vector onto another gives us a vector back. The only thing that gives us a scalar back is the dot product. and the magnitude, I guess.
Now I'll just have to drop.
Correct. Yes. And it'd always be between two vectors. It wouldn't be like you could write 3 dot v, that's scalar multiplication. But if you do u dot v, that's a dot product because it's between two vectors, not a scalar and a vector.
Okay.
Does that feel okay?
Yes.
Okay. All right. So that's half of this example. That was the hard half, by the way. The other half is that we want to express u as the sum of two orthogonal vectors, one of which is this projection. So what I can say is that I want u to equal like u1 and u2, or u1 plus u2. Excuse me. Well, I know vector u, right? Vector u is the vector 3, 1. That was given to me. One of these two orthogonal vectors in the problem we're told should be this projection. So there's that. Now to find vector u2, I can just subtract that vector from both sides. So over here that cancels out. And I'm left with just u2 on this side. Everybody okay with that? Now if I do 3 minus 21 over 13 and 1 minus a negative 14 over 13, oops, that's 13. That's going to give me my new vector. So to subtract 21 over 13 from 3, what do I need to have? Common denominator. What would the common denominator be in this case? Good, it would be 13, so 3 becomes 39 over 13. And 21 minus 39 is 18. And then similarly, to do 1 minus a negative 14 over 13, again, we need a common denominator. Hopefully it's not hard to see that that's going to be 13, so 1 becomes 13 over 13. And 13 minus a negative 14 is the same as 13 plus 14. So I'd have 27 over 13. Okay. Is everybody okay there? So what I can say then is my vector u should be my projection vector plus this vector u2. Let's just check this arithmetic really quickly to make sure that this makes sense. Okay? So I'm going to use my calculator to do this. So the first thing I want to do is make sure if I add 23 over 13 and 18 over 13, I get the x component for vector u, which was 3. I do. Then I want to check that if I add its y components, negative 14 over 13, and then plus 27 over 13, that I get the y component, which was 1. I do. That's good. The other thing I want to check is to make sure that these two vectors are actually orthogonal. So to do that, I'm going to calculate the dot product of these two vectors. So I'm going to multiply the x components together. And then add them to the y components multiplied together. and see if I get 0. I do. So this last step that I did on the calculator, this is just me checking my work. There's 2 checks that I want to do. I want to check to make sure these 2 vectors add up to give me u. That's easy to check. And then I want to check to make sure these 2 vectors are orthogonal. I'll do that by taking their dot product and making sure that I get 0 as a result. Okay? So this is going to be my final answer here. That's vector u, represented as 2 orthogonal vectors, one of which was the projection of vector u onto vector v. That was our first vector we've written there. Is everybody okay with that? Kendall? So this is what I wanted to do. I wanted to write vector u as the sum of 2 vectors. One of those vectors was my projection. So to find the other vector, all I did was subtract that projection from both sides, like I'm solving an algebraic equation. Yeah, exactly. Like if I have 7 equals x plus 3, well, to get x, I just subtract 3 from both sides, right? Same idea here. Just instead of subtracting 3, I'm subtracting a vector instead of just a scalar. Is that okay?
What happens when you cross out?
Well, that's because when I subtract it from the same side, they cancel out.
Oh, you're just demonstrating the...
Yeah.
Right.
So like when I do this, that goes away,
Yes.
and I'm left with just the x on that side, which is all I'm doing there. Does that feel okay? Okay. Again, if I write something down and you're not quite sure, if it's confusing or whatever, stop me and we'll go talk about it some more. Rest assured, if you think it's a question, you're probably not the only one that's unsure about what's going on. All right. So, this process that we've just outlined here numerically can be quite valuable in a physics class, particularly when you're dealing with forces. Because what do we know about forces, in particular forces involving gravity? That there's a force equal and opposite to that, pointing directly back at it. Right? So you guys remember that, those of you that are in physics? Would we call that force? It's the normal force, I think. Is that right? Yeah. Okay, that's what we're talking about. So where this kind of a problem becomes really difficult, if everybody's standing on a flat surface, it's no big deal, right? The force is just opposite that due to gravity. If you're standing on an incline, though, the normal force is sometimes a little bit difficult to come up with, right? That's where this vector projection idea can be helpful to us. So there's a common kind of setup in physics where we ask story problems involving, like somebody, like a crate sliding down a ramp or somebody sliding down a hill. These are common like physics problem setups. And we can use this idea of vectors and projections to deal with these kinds of problems in a way that's a little bit more like formulaic than maybe the standard physics interpretation of doing this sort of problem is. So let's look at an example. Okay, so if Kyle is sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? Those of you that are in physics, this should sound kind of as a familiar problem type setup, right? And these were rather challenging physics story problems, right? This involves drawing a lot of pictures, and you have to get like these vectors in the right spots and all this mumbo jumbo. And then you like, oftentimes I think in physics they like to tilt the axes. Do you guys do that? Do that annoying trick? It drives me crazy as a mathematician. It's like, why are we doing all this work just to get around having to do like a sine and a cosine every once in a while? Like, it seems like way not worth it to me. So let's work on this, okay? So what I'm going to start by doing is sketching a little bit of a picture of the situation. So I'm going to draw just my standard XY axis. So here is Kyle sliding down the hill. So this is like my 25-degree angle here. I'm going to call this vector V. So what I want here is to project this vector U, that's my force due to gravity, onto vector V. So this was like the vector W that we drew in the picture. So this spot here is like my projection of V, or of U onto V. So I'll zoom in there, make it a little bit easier to see what's going on in my picture. So we're saying that U is equal to force of, well, it's really going to be the weight of Kyle in the sled. Is that how you spell Kyle? That's the same as our force due to gravity in a physics class, right? That's just pushing straight down. Gravity always acts straight down, right? Okay. So we're going to say vector V then is the force acting down the hill. Everybody okay with that idea? Okay. So in this problem, we're asking for what amount of force is sliding down the hill. Notice in this problem, it's not asking about a direction at all. All it wants is the amount of force, right? So what we're looking for then is really just the magnitude of the projection of vector U onto V. That's all we need. Everybody okay there? So this is what we're trying to what we're going to be trying to calculate. So in order to calculate the projection of u onto v, I need to know the value for vector u and the value for vector v, right? Everybody agree with that? So for vector u, this is quite easy. Look at where vector u is at. Does vector u have an x component? It's just 0, right? Because it's on the y-axis. And because it's pointing down, what is going to be the sign of its y-coordinate? Negative. And I know that the weight is the same as your force, so this can just be negative 165. Is everybody okay so far? All right. So I want to go back and justify what I'm about to do just a moment, or for just a moment, by looking again at this generic formula for the projection and thinking about a little bit about what we're really doing here. So in order to get this vector, all we're really taking from v is its direction. That's really the only part of this that we really need. The magnitude of v, strictly speaking, doesn't really matter to us because the result of this projection is just going to get longer or shorter, but it's always going to be in the direction of v, right? Since u dot v over the magnitude of v squared is just a scalar, right? And if we scalar multiply to v, whatever the result of this projection, it's going to be in the direction of v anyways. It always has to be in the same direction of v. The only thing that's going to change about that is the length of how long v is. Everybody okay with that idea? Or how long it is, how much of v we're taking? Right? Look at the picture up here. Right? We're just taking some part of v, but it's going in the same direction as v. Yes? So when we come down to do a story problem like this, all we really need from v is its direction. We don't actually need a magnitude here on v. We can just assume the magnitude of v to be 1. And we're going to do that because it makes it convenient for the calculation to just assume the magnitude is 1. So what I need to calculate its direction is I do the magnitude of v, cosine theta, magnitude of v, sine theta, right? That'll give me my vector v. Everybody agree with that? That was the formula we used to resolve a magnitude and direction in the component form, right? So this is my angle theta right here that I've drawn in the picture. So that quadrant is 90, 90, 90, and then what is this part from the y-axis to vector v? Not quite. So if this angle here is 25, I know because of the alternate interior angles theorem that that angle is 25, which means that this angle here is 90 minus 25 or 65.
So it's not like the same thing as like.
Was it the same thing?
Yes.
Okay, I misunderstood what you had said then. So we would have 335 is what theta is. Everybody okay with that? And I just did that by counting around, basically, right? Nothing complicated there. So I can say that my vector v then is 1 times cosine of 335, 1 times sine 325. So if I go back here to my projection formula, I'm going to get let's do it in steps. Never mind. Let's do it in steps. So if I do u dot v, it's going to be 0, negative 165 dot cosine 335, comma sine 335. That's going to be 0 plus negative 165 times sine 335. Or just negative 165 sine of 335 degrees. I'm going to leave it like that for a moment. We're going to type that into our calculator, but I'm going to hold off on doing that right now. Now the vector, the magnitude of vector v squared, well, we just assumed was the magnitude of vector v was 1, so the magnitude of vector v squared is just 1 squared or 1. Okay. So now when I write my projection, I have negative 165 sine 335 over 1. I'm not going to write the over 1 part though. And then I'll have this times my vector v, which is cosine 335, comma sine 335. And now I'm going to go to my calculator to do this. So negative 165 times sine 335. And when I multiply that to the first component, which is cosine of 335, I get 63 point yada yada yada. And then when I do 165 sine of 335, oops, times the other component, the y component, which is sine 335, I get negative 29 point yada yada yada. Let's call that 20, I guess. And negative 49. That. So then to find the magnitude, that's all that I have left to do. It's the square root of the sum of these components squared. So I'll just do that in my calculator. So I have this piece squared plus, then I need to make sure I put the other one in a parenthesis since it's negative. I've got to be a little bit careful there. And that gives me 69.73. And since all my force units were in pounds, this guy's going to be in pounds as well. Questions on what we've done here? Let's do another example here. And then this other example where we made this assumption that the magnitude of V was 1 in this problem. We will not be able to make that same assumption in this other problem because of the type of information that was given to us. And let me kind of run through that other example so we can kind of see the difference in the problem setup. Okay? Okay. So here we have a crate that's being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. assuming the crate is of negligible weight, what amount of force is directed up the ramp? Actually, let's not draw it that way. Let's draw this. So here's my ramp, right? The crate on the ramp. And if this is like the horizontal, that's like 40 degrees that we're pulling. With that 100 pounds of force. Notice that that angle in which we're pulling the crate is not exactly the same angle of the ramp. Right? It's not pulling it directly in line with the angle of the ramp. So that's kind of the setup for our problem. Is everybody okay with that idea?
Is the angle of the inside of the triangle the bottom left angle? So that's 14.
No, definitely not. Okay. So what we have here is this guy's like our vector v, and this guy is like our vector u. So we want to like project down here. That's kind of what we're doing. I made kind of a mess out of that. It's hard to read it. I apologize. Let me zoom in a little bit. Okay. So the blue is my projection. Is everybody okay with the drawing? Okay, so I want to do the same thing. I want to calculate the magnitude of this projection. But here we're giving actual, real good information about this vector v, right? In the previous problem, we weren't given a lot of information that we could assume about a vector v. Here we have lots of information about v. Since we're given like a length and a height for the ramp, it's easy to see that the vector v is going to be the vector 10, 2. Is everybody okay with that? That was just like the horizontal part and then the vertical part. That's going to describe that vector v, the red line that we've drawn there. Everybody good there? Okay. Now, for my vector u, I know the magnitude of u is 100, and the angle for u is 40 degrees. So if I take those together, u is going to be 100 cosine 40, and then 100 sine 40. Everybody good there? Now if I look at my projection, to do that I need u dot v over the magnitude of v squared times vector v. So I'm going to do this in 2 steps. I'm going to calculate u dot v, which is going to be 10 times 100 cosine 40 plus 2 times 100 sine 40. Everybody okay there? And then to calculate the magnitude of v squared, well, the magnitude of v is just going to be the square root of 10 squared plus 2 squared. And if I square that, we get 104. Everybody okay there? So, if I go ahead and do this then, I'm going to take, we'll write it down here. We're going to have 1,000 cosine 40 plus 200 sine 40 over 104 times the vector 10, 2. And I'm just going to do that on my calculator. So we have 1,000 times cosine of 40. Oops, let's do it as a fraction. 1,000 cosine 40 plus 200 sine 40 over 104. And then I need to multiply that by 10. So that gives me 86.02 for my x component. What's up?
To the right, is that 10 to?
10 comma 2. Yes, that's my vector v. And then I'm going to do the same thing, except instead of multiplying by 10, I'm going to multiply it to the y coordinate, which is 2, which gives me 17.20. Everybody okay there? And then to get the magnitude, I just do the square root of these two things squared. And that's it. So this guy squared plus this guy squared. So I get 87.72. Now, David, you asked the question about the angle of the ramp being 40 degrees also. If the angle of the ramp was also 40 degrees, we'd expect the force to be equal to the force pulling the crate, to be 100 pounds. Here, because that angle isn't directly parallel with the ramp, you're not getting all 100 pounds of force going in the direction of the ramp. You're getting some of it like being pulled up or down. I'm not sure what the angle is, but some of that force is being directed either into the ground or up into the air. You're not getting it in perfect line with the ramp. Okay. So we'll stop here. So this time, we are ready to do problems 41 to 50. This will be the last homework set from this chapter. So this is going to be the last set of topics we're going to work on here in this chapter. So next week we'll be looking to find a test date for this chapter 2. We'll take at least one more day to kind of recap and kind of go through some examples and work on the study guide and that sort of thing. I'm going to post